Hello everyone, and welcome to this demonstration on building a custom Linux kernel and configuring the NXP Wi-Fi Bluetooth driver for regulatory support on Murata modules. Let's first understand the different scenarios for regulatory support. In Murata-only regulatory support, we overwrite the default regulatory support of the Linux kernel, making it ideal for projects that exclusively use Murata modules. This is what we'll cover in detail today. The default regulatory support is the baseline provided by the NXP-Based and does not include any customizations for Murata modules. It's straightforward and requires no additional steps. Finally, the merged regulatory support combines Murata-specific support with the kernel's default regulatory settings. While useful, this requires additional configuration steps. For further guidance, you can refer to the Murata user guide or reach out to the Murata community forum. Before we begin, have the following prerequisites in place: a Linux build environment set up with the necessary toolchain, get installed on your system, as it's essential for fetching source files, a hardware platform for loading and testing the software. For this demo, we are using the NXP-i.MX8 DXL EVK. The Murata Wi-Fi Bluetooth module set up with your hardware platform. In this demonstration, we are using the Murata 1XLM 2 EVB connected via the M2 interface. Now, here's an overview of the steps we'll be walking through in this video. First, we will build the Linux kernel for the target platform. Next, we will update the kernel with Murata regulatory solutions and rebuild it. We will also build the modules. Next, we will compile the NXP Wi-Fi Bluetooth driver against the modified kernel. Once all the artifacts are ready, we will deploy the kernel, modules, and driver to the target platform. Finally, we will load the driver and verify the regulatory solution is working as expected. Let's quickly look at the output for the default regulatory configuration. Without any changes or driver loading, the default settings allow users to set various regions. For example, here we see the output from the NXP-i.MX8 DXL with the default demo BSP image. This is a useful starting point for understanding how the kernel handles regulatory settings and what changes the Murata solution introduces. Specific commands like iwregget and iwregset allows the user to query and modify these settings. As shown here, setting the region to US updates the supported frequency ranges and power levels. First, we need to install the cross-compilation toolchain. This will allow us to compile the binaries for our ARM64 target board. Do note that this requires superuser permission to install. This command installs the GCC ARM64 Linux GNU package, and it includes everything we need to cross-compile for ARM64 EVKs. Now we will export a couple of environment variables so the build system knows which architecture and compiler to use. The arch equal to ARM64 specifies our target architecture, and the cross_compile equal to arch64 Linux. GNU tells our and build tools to use the ARM64 cross-compiler. Let's keep all our work in a dedicated folder. This will be easier going forward. Next, we will clone the NXP-i.MX Linux kernel from GitHub and check out the branch we're going to use. This will take some time since the kernel source is quite large. Once the download is completed, before we start the build, it is important to store the kernel directory in an environment variable named kerneldir. This is important for the driver when we build that later, as this is the environment variable the driver will use and build against. Next, we will load the default configuration for the i.MX8 platform, and then we will start the build. This step will take some time depending on your system hardware. Once the build is complete, we need to fetch Murata calibration files. We'll place them in a separate folder. These calibration and regulatory files will be added to the kernel to ensure proper Wi-Fi operation. In the next step, we need to copy the Murata.hex file for 1XL module into the kernel source tree. The .hex file contains the calibration and regulatory data specific to the Murata 1XL Wi-Fi module. Including this file in the kernel build process ensures that the module operates within the correct frequency and power settings required for compliance with regulations. Now we will jump back to our kernel directory once again and rebuild. This will once again take some time to complete. The build is complete. We will install the kernel modules into a temporary folder now. Next, we will compress the modules to create a tarball so we can easily move them to our board later. The next step is to build the NXP Wi-Fi driver. Let's clone the source and build the driver. Once again, it is important to have the kernel-dir environment variable set to our customized kernel before starting the build. The driver will be built against this kernel. Finally, let's create a target folder to store our generated artifacts that will be transferred to the EVK. We will copy the kernel, the module's tarball, the driver binaries, and the downloaded Murata regulatory files to this target folder. On the EVK, running the 6.1.36 NXP Linux demo image in this example, we have copied over our target folder. We used a flash drive to copy over the files. You can also use SCP. We have all the artifacts here: the kernel image, the modules, the Murata calibration files, and the driver. We will now place the files in the respective locations on the EVK's file system. First, we copy the kernel image to the boot partition. The next time we boot the EVK, this new kernel will come up. Next, let's move the regulatory files. And finally, we should place the modules in the modules directory and extract it. We can keep the driver files where they are. Now, when the EVK restarts, it will use the newly installed kernel image and modules. Reboot the EVK. Once the system has restarted, let's check the kernel version to make sure the new one is loaded. Next, we will load the driver. Afterwards, we will configure the correct regional settings for our module. The switch region script copies the appropriate regulatory files for our chosen region to the correct locations. The changes are not applied until the system is rebooted. So, let's reboot the system. We can now confirm the regulatory domain is getting set correctly. And here you can see the values are different from the default ones we saw earlier, and this reflects the correct regulatory values for the Murata 1 XL module for US region. And that's it! You've now successfully built and deployed Linux kernel and modules with Murata regulatory solution and tested the changes.